Hello, I welcome you all in this course on power plant engineering. Today we will discuss about the impulse steam turbine. Now, steam turbine is one of the turbine which is used in power plants. So, today we will cover the flow of steam through impulse turbine blades. As you know, there are two types of turbines, impulse turbine and impulse reaction turbine. So, today we will focus on the impulse turbine blades. We will draw a velocity diagram for impulse turbine blades. We will discuss about the blade and gross stage efficiency, influence of steam ratio on the efficiency of a steam turbine, impulse steam turbine. We will discuss about the impulse blade section, and at the last we will discuss a little on twisted blades in the steam turbines. Now, in a steam turbine, the power is developed, as all of us know, and all the thermal power plants, they work on Rankine cycle. If you draw the Rankine cycle on the temperature entropy diagram, the ideal Rankine cycle is going to be like this. So, here the expansion of steam takes place in process 1 to 2, and 2 to 3 the condensation of steam takes place, 3 to 4 pumping or increasing the pressure of the working fluid, that is water, and 4 to 1 heating in the boiler. So, in the entire cycle we get output only through process 1 to 2, that is the work output. Otherwise, in process 3 to 4 also there is work interaction, but here work is done on the system. So, in the entire cycle we get work output from the steam turbine. And steam turbine, as you know, normally steam impulse turbine or impulse reaction turbines are used in the power plants. Nowadays, the application of impulse reaction turbine is more, because they have certain advantages over impulse reaction turbine, which I have discussed in the previous lecture. So, here we will draw the velocity diagram. Velocity diagram means what should be the direction of the velocity, so that the steam does not strike the turbine blade, because if the steam strike the turbine blade, it will damage the turbine blade, because the velocity of the steam is approximately 1100 meters per second. Though it is not constant, it varies from, let us say, 800 to 1200. It varies from design to design, but it is quite high, and this velocity is, it is obvious, it is a supersonic velocity. When we are having a supersonic velocity and this velocity is attained in a convergent divergent nozzle, and certain formulas are used, that is how we get the velocity at the exit of the nozzle. Now, with such high velocity, steam strikes the blade. Now, steam does not strike the blade, it glides over the blade, and there is a change in the direction of the motion of the steam. Steam is entering from this side and leaving from the other side, right? And blade is not fixed, blade is also moving with the certain peripheral velocity u. Since the blade is moving, steam has to glide over the blade. So, first of all we have to decide what should be the nozzle angle, at what direction the absolute velocity of speed of the steam should come, so that it strikes the blade. So, we will have to draw a relative velocity diagram, right. Now, regarding u, peripheral velocity of the steam, u is calculated by pi dn by 60. D is the diameter of the drum, because all the blades in a turbine, they are mounted over a shaft. So, we take the mean diameter, and this diameter is used here for finding the peripheral velocity. N is the RPM. So, normally in a single stage turbine RPM is quite high, but if you take the multi stage turbine, RPM is approximately 3000 approximately. So, we can easily get the value of u. Now, steam should glide over the blade, as I said earlier. So, we will say that vector V1 is V1 minus vector u should be equal to vector VR, relative velocity vector, right. So, vector V1 is equal to vector relative velocity vector plus peripheral velocity vector. So, in this vector, if we add this peripheral velocity vector, we will get the V1 vector. right? And this angle is known as blade inlet angle. Sorry, the nozzle inlet angle. And this angle is known as blade inlet angle. Similarly, on the exit side, when we go to the exit side, this is VR2, right? This is the relative velocity with which the steam is leaving the blade. Now, in this case also, the V2 absolute velocity at outlet is equal to, this is R1, VR2 plus U. Now, here also if we add the peripheral velocity, we will get the absolute velocity, right. Now, these two triangles, they are transformed on a single base, that is U. This is peripheral velocity. This is VR1, relative velocity. Now, this is going to be the absolute velocity at inlet, as you can see here. We have just transformed the vectors. So, we have drawn one vector parallel to this, and we have drawn one vector parallel to this from here, one vector parallel to this from here, and we have simply drawn this triangle. Now, this is obviously blade inlet angle, which is denoted by beta, and this is nozzle inlet angle, which is denoted by alpha. Now, if you look at the exit side also we have this VR2 U and then V2, and for this also we can draw a triangle like this. This is VR2 and this is V2. So, VR2, this is angle known as beta 2 blade outlet angle, and this is nozzle outlet angle. Now, nozzle outlet angle is important in the case when we have to do multi-stage designing of the turbine, right. At what angle the steam is coming out of the previous stage, and then it has to be reoriented, and then it will go to the next stage. Okay. So, now there is a loss, because ideally there should not be any loss, but there is a loss in the course of travel over the blade surface. So, relative velocity reduces in practice. So, this is known as VR2 is equal to K VR1. This is known as blade velocity coefficient. KR2 is known as blade velocity coefficient. And this velocity is, there is also one velocity factor, that is VF1. This is VF1 is nothing but V1 sine alpha 1, or we can say VR2 sine beta 2, both are same. VR2 sine beta 1, sorry, no, this is not beta 1, or V1, sorry, not BR2, VR1. So, it is VR1 sine beta 1. So, this is velocity of flow. Similarly, on this side, exit side, we can find the velocity of flow as VF2 is equal to VR2 sine beta 2 or V2 sine alpha 2. Now, this has to remain constant. A good designer should ensure that this component of the velocity remains constant. It means VF1 should be equal to VF2. If this component is not constant, there is going to be axial thrust in the system. Axial thrust means there is a turbine shaft, right, and there is a thrust in this direction along the axis of the shaft. When there is a thrust on the axis of the shaft, it may damage the turbine. There so many things can happen. In fact, it is going to be accidental if there is a net thrust along the axis of the shaft. So, it has to be avoided, and a designer should ensure that VF1 is equal to VF2. This is only possible only when the steam glides over the turbine surface. Now, output of the turbine, force. How much force is being exerted? Now, force is change in momentum. Now, if you draw the velocity diagram on this side, you will draw a velocity diagram. This is V1, VR1, beta 1, beta 2, VR2, V2 and U. Now force F. F is change in the velocity. This is known as VW, wind velocity. Now F is change in velocity, right? Sorry, change in momentum, rate of change of momentum, not change in velocity, rate of change of momentum. So if we assume that there is a flow of 1 kg per second, so it is going to be change in the velocity. F is equal to m delta V. So if we assume m is equal to 1, then it is going to be the change in velocity. And which velocity? Velocity which is with component of V1 which is causing force on the blade, which is causing force in this direction, direction of U of the blade. That is V1 cos alpha 1. That is a component which is causing force in this direction. Now in the same direction, change in now minus V2, this is alpha 1 and this is alpha 2. Component of the velocity which is causing force on the blade. So it is going to be minus V2 cos alpha 2, not beta alpha, it is going to be alpha. So it is going to be V1 cos alpha 1 minus minus V2 cos alpha 2, this is alpha 2, right. Now V1 cos alpha, we can say it is will component of 1 inlet, this is the will component, and V2 cos alpha 2 we can say it is will component of exit. So it is going to be VW1 plus VW2 and that is known as VW. Now if the mass flow rate is m dot, so definitely the force is going to be m dot VW. The blade is moving with the velocity u, right. So it is going to be, so if you want to find output, then F into U m dot VW U, that is going to be the output of the turbine. Now with this, if you divide this by 100,000, we are going to get output in kilowatts. That is how we can calculate or we can find output of the turbine using the velocity diagram. Now every turbine has certain efficiency, every machine has certain efficiency. So is the case with the steam turbine also. Steam turbine has certain efficiency and which is known as blade or diagram efficiency. Blade, either we call it blade efficiency or we call it diagram efficiency. Now blade efficiency is work done by the blade divided by kinetic energy of incoming steam. Now what does it mean? It means steam is coming with certain kinetic energy, right. An ideal machine should have been, ideal turbine or ideal machine should have been which should have trapped all the energy of the incoming steam. Steam is coming from a nozzle at a velocity, let us say V1. So it is going to be the half mv square. This is the kinetic energy of the steam which is entering the turbine. Now in an ideal turbine, all this, because this is high grade energy, so conversion of high grade energy to one form to another form is very easy, right. So this kinetic energy should have been completely converted into the work output. Then we can say the blade efficiency is 100%, but that does not happen. I mean 90%, 80 to 90% of this energy is trapped by the turbine, but remaining 10 to 15% or 5% energy it goes out with the steam which is leaving the blade. In ideal condition, what should happen? It should happen something like this: steam is entering the turbine with certain velocity and there is no output velocity. Still water we are or still steam we are getting outside, then it is 100% efficiency. But practically it is not possible. Steam will leave the steam turbine with certain velocity, and this outgoing velocity will reduce the magnitude of the outgoing velocity, will reduce the blade velocity, blade efficiency. So here the formula is simple: work done by the blade, as we have calculated earlier, work done by the blade is mass flow rate Vw and multiplied by U in watts. We are not dividing it by 1000. And kinetic energy of incoming steam is half m V1 square. So simply this m will be cancelled out. And will be cancelled out, and then we will get 2 Vw U by V1 square. Now this is blade efficiency, and it is independent of the mass flow rate, right. So it is a function of component of the velocity diagram, peripheral velocity, and velocity of the velocity of incoming steam, and it is a strong function of velocity of incoming steam. Now after the blade diagram efficiency, there is another term which is known as gross stage efficiency. Gross stage efficiency. Now in a steam turbine there are number of stages. Gross stage efficiency is very important tool while designing a multi-stage steam turbine, right. So it gives us idea about how much energy is being converted into the useful work in each stage, right. So this is known as gross stage efficiency, because during expansion in a turbine, now if we draw again the Rankine cycle, during expansion. So this expansion is taking place in number of stages, because in actual practice multi-stage turbines are used, single stage turbine is not used. So if there is a number of stages, so in each stage some enthalpy drop will be taking place. So suppose there is a 10 stage turbine. So in each stage certain amount of enthalpy drop will take place, and so we are concerned with the energy only right now. So this much of enthalpy drop, how much output we are getting, that is it. Now here we should understand nozzle is also part of the system, expansion process, because in a Rankine cycle nowhere expansion through the nozzle is shown. So whatever happens in the nozzle, it is a part of the expansion process from stage 1 to stage 2. We are simply feeding high pressure, high temperature steam into the turbine, and this nozzle, diaphragm, turbine blades, they are integral part of this process 1 to 2, right. So here in order to find the gross stage efficiency, we write first of all work in the stage, that is work output in a stage divided by enthalpy drop in a stage. There are two things: work output in a stage divided by enthalpy drop in a stage. So work output in a stage, we have already calculated mVWU, that is work output in a stage. Enthalpy drop delta H. This is the gross stage efficiency. Now it can be further modified, because this enthalpy drop, basically this enthalpy drop is in nozzles, where this enthalpy change in enthalpy is converted into the kinetic energy, right. So if we look at the nozzle efficiency of the nozzle, if we talk about the efficiency of the nozzle, it means efficiency of the nozzle reflects that what is the enthalpy drop in the nozzle and what part of this enthalpy drop is being converted to the kinetic energy. Because nozzle simply converts, because if you consider nozzle as a control volume, this is side 1, this is side 2, and if you apply the first law equation, H1 plus V1 square by 2 plus gz1 is equal to h2 v plus v2 square by 2 plus gz2. If it is a horizontal nozzle, this will be cancelled out. V2 is much higher than V1, exit velocity is much higher than V1, inlet velocity. So this can also be considered 0, or it is negligible in comparison to V2. So V2 we get is under root 2 H1 minus H2. And while doing calculations, this is a normal mistake by the students. They take enthalpy in kilojoules, right? And then they multiply difference multiplied by 2 under root. It should not be like this, because velocity is in meter per second. So if you are taking enthalpy in joules, only then you will get correct answer. So enthalpy drop. Now this enthalpy drop, what part of this is being converted into the, because nozzle has some internal frictions also, internal losses also. So what, or and heat transmission to the surroundings cannot be denied, though it is negligible in case of nozzle. That is why we consider flow through nozzle as an adiabatic flow, because for controlled volume remains inside the nozzle for a very short duration of time. Okay. So the nozzle efficiency, we can say that output energy going with the outgoing steam, that is half m V1 square, that is steam which is leaving the nozzle, divided by enthalpy change delta H, right, and multiplied by m, of course, because this is specific enthalpy. Now we know that blade efficiency is also something like that, VWU m divided by half mV1 square. Now if we multiply this blade efficiency by nozzle efficiency, efficiency of the blade and efficiency of the nozzle, what we are going to get? We are going to get m VWU divided by m delta H, this is small h, delta H, and this m will be cancelled out, and we will be getting VWU by delta H. So if you want to have gross stage efficiency, then simply we can multiply these two efficiencies, we will be getting gross stage efficiency. Now the next thing is influence of blade speed ratio. Blade speed ratio. As we discussed earlier, the blade speed ratio is U by V1, peripheral velocity divided by inlet, absolute inlet velocity, and it is denoted by rho. If you look at the velocity diagram again, this is V1, VR1, V2, sorry, this is U, VR2, and this is V2, right, and this is VW, this is beta 1, beta 2, alpha 1 and alpha 2. Blade efficiency is 2 VWU by V1 square, right. Now if we increase, how this speed ratio is going to affect the blade efficiency, because this speed ratio is also very important parameter while designing a turbine, right. So blade efficiency is VWU by V1 square. Now this can further be modified as, because VW is, you can always take, this is VR1 cos beta 1, this is VW. So this is VR1 cos beta 1, this is VR2 cos beta 2, this is VR2 cos beta 2. So VW can also be taken as VR1 cos beta 1 plus VR2 cos beta 2, and it can also be taken as V1, as we did earlier, V1 cos alpha 1 plus V2 cos alpha 2, either way. So, we are considering this. So, if we take this, then blade efficiency is going to be equal to 2 times VR1 cos beta 1 plus VR2 cos beta 2 divided by V1 square, right. Now, here VW is, as we said, VR1 cos beta 1 plus VR2 cos beta 2, or we can take VR1 cos beta 1 1 plus VR2 by VR1 cos beta 2 by, right. So, VW is VR1 cos beta 1, this is the ratio. This we have earlier said it is the velocity ratio, which is denoted by K, VR2 by VR1. When there is no friction loss, it has to be 1, but it is never 1. It is always, practically it is always less than 1. And this is blade ratio, cos beta 2 by cos beta 1 is called blade ratio, it is denoted by V, B. Now this VB is with us. Now, if you take 2UVB, 2UVW, because 2UVW is here. So, for 2UVW, we will take 2U VR1 cos beta 1 1 plus KB. Now, VR1 cos beta 1. Now, VR1 cos beta 1 is always, if you look at this diagram, it is going to be V1 cos alpha 1 minus U, right. So, this can be replaced by this expression. So, the next is going to be 2U VW is going to be equal to 2U V1 cos alpha 1 minus U 1 plus KB. Right. Now, we have V1 here. Now, if we divide this by V1 square, this side also has to be divided by V1 square, and U is equal to also rho V1. So, V1 can also be come out from here, and we will get 2 rho, because this is U is equal to rho V1, this is also 2 U is equal to rho V1. So, we are going to get 2 rho V1 2 rho V1 cos alpha 1 minus rho 1 plus KB, because U is equal to rho V1 we have put here, then V1 will be cancelled out, right, and then we will enter in this bracket, then it will be this V1 will be cancelled out, and this U by V1 is going to be the rho. So, this is completely correct, 2U VW by V1 square is this much. Now, this is blade efficiency, right. Now, if we differentiate this blade efficiency with respect to rho, 2 V1 rho cos alpha 1 minus rho square 1 plus KB. Now, this is efficiency. Now, if we differentiate between rho, in that case we are going to get 2 V1 cos alpha 1 minus 2 rho 1 plus KB. Right, in ideal case K is equal to 1, and since blade angle, there is not much in blade angle also, beta 1 can be considered, cos beta 1 can also be considered as cos beta 2. So, in this case, if you want to maximize this value of blade efficiency, we can always take rho is equal to cos alpha 1 by 2 to maximize, because if you double differentiate this, you are going to get the negative value. If you differentiate it again, then you are going to get negative value. So, it means this differentiation we are getting at the maxima, and that is rho is equal to cos alpha 1 by 2. Now, when rho is equal to cos alpha 1 by 2, right, it means if the alpha 1 is 0, then we are getting rho is equal to 1 by 2 is equal to u is by v 1 is equal to half, right. As if you remember in the previous lecture, we found that at rho u by v is equal to 0.5, maximum efficiency is maximum, right. But here it is called cos alpha 1. So, normally while designing a steam turbine, the value of rho is normally taken as 0.45, not 0.5, it is taken as 0.55. And if you put the value of rho here, now modified value of rho here in this expression of efficiency, you will find the maximum efficiency is cos square alpha 1, right. So, this is the so alpha 1 is if it is 0, then efficiency is 100%. That is not possible. We do not take alpha 1 as equal to 0, right. So, alpha 1 has to have a certain value, and through this certain value we get the maximum blade velocity. Now, comes the shape of the blade. As I said earlier, that we will discuss about the shape of the blade also. In a steam turbine, if there is a drum, on the drum a blade is fixed, and this blade has certain like this profile like this, right, but it is not straight, the blade is twisted. The blade is twisted because what velocity diagram we draw, it is taken at the mean diagram. This velocity diagram which we have drawn, this u, let us take V1 and VR1, and this is blade inlet angle. This nozzle inlet angle is fixed, u is fixed, V1 is fixed. Now, the beta 1 will change according to the u will change according to the position. U is not fixed because u is equal to pi dn by 60. So, this peripheral velocity will change when we move from this point to this point. In a steam turbine, the height of the blade goes up to 1 meter. It starts from 15 to 30 centimeters, it goes to 1 and 1.5 meters. So, if you are moving in the radial direction, the u will change. The moment there is a change in u suppose increases, the blade angle will change. If u is reduced, the blade angle will also change. So, blade angle will keep on changing, right, when you are moving from this side to this side. For this reason, in a steam turbine, when the blades are manufactured, they are twisted. So, when you are moving in a radial direction, the blade angle will keep on changing in order to ensure that there is no axial shock or there is no shock entry, no thrust on the blade profile, and steam enters the blade profile along to the curvature of the blade. That is all for today. Thank you very much.